All right, so there we have it. So we'll take them up next Wednesday, but we will look at calling on a couple of you to work maybe one or two of these. Some of these in the front, not necessarily those towards the end, because I do want to spend a little bit more time maybe looking at some problems in class Monday, and try to start chapter 7 Monday too, okay? All right, here we go. Okay, we good? Okay, now Hooke's Law, looking at Hooke's Law, it's I think we got one slide maybe on Hooke's Law, which that's okay. Hooke's Law deals with looking at the force applied from a spring, okay? Now this, to me, is probably one of our more practical physical laws, in that it's actually something that we can create with our own hands. Anyone can make a spring. You can take a piece of wire, take a pipe, and wrap it around it. You got a spring, okay? And based on the diameter of the spring, of the wire, will determine the tension and the type of steel too. You know, if you have a real soft steel, you know, it's going to be a softer tension. If you have a steel with a lot of iron in it, more iron than carbon, then it's going to be a much stiffer spring. And of course the diameter, you know, has a lot to do with that too. Springs are something that we use a lot. I mean, you think about the hinges here in our door. Those are springed hinges. There's not hardly anything that you can think of that's made mechanically that doesn't use springs. The central heat and air unit is full of springs. You know, when you think about the ductwork, even here in the mechanical part of the actual unit itself, there's springs to open and close various parts of the system. Some are very small, some are larger. You look at the car, you got the coil springs on a car. Leaf springs. Leaf springs are actually some of the first springs made, and my God, the old Model T was just like, you know, what was the big difference between the Model T and the Model A? Well, the suspension. Model T was like, man, you'd hit a bump and it was like break your neck. The Model A, it was a much softer ride. They finally figured out that, you know, we've got to make better springs for these cars because we're breaking people's necks. I mean, really, because the roads were rough. We didn't really get good roads until probably on up into the 50s. We started getting some decent roads in the majority of America. And we didn't really start getting good roads around here until probably the 70s. You go outside of downtown Boaz, and a lot of your roads are turned into dirt. Your county roads especially. I remember as a kid, there were still a lot of county roads that were dirt roads. And DeKalb County especially. DeKalb County's just recently finally paved most all their roads. And I'm not dissing DeKalb County. I love DeKalb County. Beautiful country. I know a lot of people up there are great people. I'm not dissing DeKalb County. I'm just saying. I remember for years and years and years, there was one particular road that was very well traveled. It's dirt. But yeah, so all that to say this, springs are extremely important to us. So how do we determine the force of a spring? Now they say F of X. We could actually write this, now that's just to give us the direction, okay, and it doesn't have to be horizontal, it can be vertical. I like to say the force of the spring is equal to the spring constant, K. Now K is your spring constant. That is the spring constant, okay, you need to know that. That's the spring constant. And then of course X, or we could say what? S. We could say S, all right, if you wanted to. The spring constant times the displacement of the spring, okay? And so we produce a force in newtons. Now the spring constant, the units for the spring constant are going to be what? Newtons per meter. Newtons per meter. The meters cancel out and we're left with what? Newtons. And by the way, typically when we write Hooke's Law, it should be written this way. I'm kind of surprised the book didn't write it this way. It should be written this way. All right, I'm going to erase. You got it? All right, I'm going to erase. It should be written this way. Okay, and why negative? Okay, what do we know about a spring? If I take a spring and stretch it, what will it do if I let it go? It goes back, don't it? Unless I sprung the spring. Yeah. In other words, if I go beyond its stretch limit and you sprung it, okay? In other words, it's lost its ability to go back to its original position. Okay, now, that's called a sprung spring. All right, anyway. Okay, so what does that mean? That does not mean the spring constant's negative. That means that we have a what? A restoring force back this way. Okay? So the negative represents the restoring force of the spring. Okay? So it actually should be negative kx. Okay? Now remember, again, all that negative tells us is that the restoring force of the spring is in the opposite direction of the force applied to the spring. If you compress it, the restoring force is opposite. If you stretch it, then it's opposite. Okay? All right, now, and so I'm really shocked they didn't put that in there. Anyway, they didn't. Okay. But it should be. Okay, now what we can do is we can take this equation here, and they show you on page 184, and I'm going to try to hurry, y'all, because I know we want to work some problems and then let y'all go. You can take this equation. We can take our work equation. Now, I love this. Remember, work is what? If we integrate work, now, remember we're talking about a non-constant force. We got x final and x initial is the force dx, right? Okay, take that and put it right there and integrate it. Okay? If you take that, substitute for force, then guess what we get? We get the work done on a spring. And if we do the integration, now I don't need to do it, y'all can do it. If you integrate, because it becomes what? Work is equal to the integral, x final, x initial, of what? Kx dx, and we integrate with respect to x, guess what we get? Well, we get that right there, y'all. We get work is equal to 1/2 the spring constant times, notice they put x capital. Well, okay, it's just the displacement of the spring. Okay, that's all it is. Squared. All right, and that comes from the integration, if any of you want to know where that comes from. So there's your equation. So we got two equations. We got Hooke's law. This is Hooke's law. Please write it down as that. Hooke's law. Right there. Hooke's law.
Do you want us to write it with a negative?
Yes, put the negative in there, okay? Okay? Because the restoring force of a spring, now if I just ask you, what's the magnitude of the force of this spring, then you're going to give me a positive answer, right? Remember, magnitude is always positives. If I just say, what's the magnitude? So, we don't want to get all crazy with this, but it really is supposed to be negative because of the restoring force of the springs in the opposite direction. That negative means opposite direction. So Hooke's law, and we got what? This is the work. Actually, that should say a spring right there. Work done by a spring is 1/2 kx squared, okay? Now this is a beautiful equation to use, and it's very easy to use because remember, y'all, the work kinetic energy theorem is work total or work net. Now remember, we put net there is equal to what? Well, it's equal to delta K. Well, guess what? We can substitute this right there. So if we know the spring constant and then we know how fast something's moving, guess what? We can do delta K here, but then we can, if we have a spring that's moving or an object that's moving that hits a spring, okay, we can determine the final velocity or the initial velocity, excuse me. Because we know when it's completely compressed, what's the final velocity? If I completely compress, if an object hits a spring and completely compresses it, what's the final velocity? 0. Yeah, I think you said that. Okay, all right. Okay? So we don't forget, y'all, you can do some substitution here, and I assigned some problems where you're going to do that. Okay, all right. Any questions on that? Oh, by the way, what are the units? All right, what's the units here? The units here are newtons, right? Units here are newtons. Units for force, excuse me, woo, about to make a boo-boo. All right. Pointed at the wrong thing. We know force is always what? Newtons, right? I'm going to throw this pen in a minute. And of course, what is the unit for work? It's joules, right? Always joules, right? Okay. Okay, good. Now, all right, let's move on. All right, but what about the work kinetic energy theorem for a curved path? Now, boy, here it gets a little squirrely. Not too bad, though. Okay, we see it's still the dot product, but we integrate. Notice that we can throw the angle in here, okay, between the force and the what? L is the what? Length of the curved path, okay? All right? Or we can just do what? If it's parallel, if the component of the force is parallel to the motion or the path it's following, then we integrate what? We integrate the force with respect to L. Okay? All right.
So, which one of those would you recommend more?
I would be familiar with, let's see, that's the fourth time. I would be familiar with this one because we may have an angle at times, but also that one too. Well, this one and that one is really the same thing. Well, except here it's not parallel.
If we had to only do one, we just need the middle one because it does it all.
Yeah, it actually does it all, yeah. Yeah. And of course, if the cosine was 0, okay, then it's 1. But what if it's cosine of 5 degrees? Well, it's still close to 1. So we just throw in cosine of 5, okay? So yeah, that would be your most useful. Okay. All right. Okay? And I probably will give you one problem with this, maybe. Okay, because the curved path does change it a little bit. Okay. All right. I want to get to power now. Okay. All right, here we go. Power. Power. Now, we've talked about newtons. We've talked about what else? We've talked about, well, meters per second squared, newtons, unit of force, joules, unit of energy. Now, when we get to electricity, what is electricity? Now, I know I'm jumping ahead, but that's okay. I'm going somewhere. Well, electricity, electrical current, we actually, or voltage. Let me ask you this. What is voltage, V? Voltage is actually the work done on the charge. Okay? The work, the number of joules done per coulomb. It's the work done on the charge. If you think about it, if you've ever heard anyone talk about electrical current, you'll always hear them say, 220 will knock you down, 110, 120 will cause you to go into a state of tetanus, stick. And that's true. Actually, 120 is more dangerous than 220, 240, or even higher, because it will cause your muscles to go into a state of tetanus, whereas 220 has higher voltage, there's more work per unit charge, it will literally knock you down. Because why? Because there's more work doing literal work on the charge, the electron. 120, 110, there's not as much, so what happens is your nerves go into a state of tetanus, they lock, and people have died, been electrocuted on 110 because they get a hold of it and they can't let go. Their muscles lock. Whereas I've heard of people working on 220, working for Ace Hardware, yeah, I was wiring up a dryer plug hot. We were in a hurry and we didn't cut the breaker off. Well, they get into a hot wire, they grab those two hot legs, and next thing they know, they're back about 3 feet from the dryer laying on their back. And the guy working with them says, yeah, man, it knocked you back. It literally will knock you down. People on power lines get hit with these high voltage, and some people have survived, some die. they'll get into these electrical entrances. Now that's 220 at 200 amps, y'all, which it ought to kill them. But by the grace of God, it didn't. I've known of people actually accidentally touching the entrance wire coming in their home. And next thing they know, they're on the ground, you know. It literally knocks them off the ladder. Okay? Very high voltage and high amperage. Amperage is what really kills you more than the voltage. Okay? So again, I said all that to say this, it's the work. So where does that lead us? Okay? When we look at the rate, and notice, I said rate, didn't I? Well, guess what that's going to lead to? It's going to lead to a derivative. So the rate done on the work is power. Now, if we just want to know the average power, we can notice the change in work divided by the change in time, and we get what? We get watts. Please remember what a watt is. A watt is the 1 joule per second. In other words, it's the amount of work done in 1 second. 1 joule done in 1 second. 1 joule of work. But we also have horsepower. Another form of work. Power, excuse me. And notice, and I do want you to remember that conversion. Please write that down on your cheat sheet. Okay? Now, you know when we say rate, you know when you hear the word rate, guess what you're going to have? It's going to be a derivative. So if we want to know the instantaneous power, then we're going to take the derivative of the work with respect to time. Okay? Now again, notice this is over a very short time interval. In other words, as the time approaches 0 or as the time approaches 1 second. At 5 seconds, boom, what is our power? Not at 4.9 or 5.1, 5. Okay? All right.
The W in this by the 746, is that watts or work?
That is watts. That is watts, yeah. This is watts. W, I'm glad you asked that. That's watts, okay? So 1 horsepower is 746 watts. Now, that's the conversion. Now, if I come in here and I plug a VOM meter in my outlet, what am I going to be reading? Average or instantaneous? I'll just stick it in there and leave it. Probably average, won't it? Because what's going to happen to that meter? It's going to fluctuate, isn't it? Has anybody ever done that? Anybody ever watched a VOM meter? You don't get straight 120 all the time, do you? If you'll stick a VOM meter in one of these outlets, it'll probably hit 120 and then it'll probably drop down to 118 and it might go up to 121 and it'll drop back down to 119. Might even drop to 115. Eee. All right? And if it gets down to 110 or 105, we got a problem. My dad, when he worked here on maintenance, they were burning out compressors over here on the big walk-in cooler at the cafeteria, and they'd burned out like 2 in like a year. Well, I mean, that's just unheard of. I mean, you just don't do that. Dad said, there's not enough voltage. We don't have enough voltage / amperage. So he took his voltmeter, and sure enough, he checked it, and it was like 190. And it was supposed to have been 220 at least.
It's actually said that Paul and Boaz is something.
Who did?
Actually said that.
Really? Yeah.
Walk-in cooler.
Low voltage? Yeah. And it's going to burn the compressor out because the compressor is built to operate at 220. And sure enough, it was 190. And Dad checked it again, 190. And then another time maybe like 195. And another time 190. And he called Marshall Cab. He said, look, y'all got to get over here and replace this transformer. Because if you ever look right behind the cafeteria, there's a bank of transformers, right, 3 on a pole. He said, we got a bad transformer. We're burning out compressor. He said, come over here and check the voltage. And sure enough, they said, well, Melvin, you're right. And so they replaced the transformer, fixed the problem. So, you can find problems that way by checking your voltage. Another good example. Gummit. Copy machines. They want continuous voltage. Those things are $15,000, $20,000. So we have a voltage regulator hooked to ours. They want a continuous flow of voltage going to that copy machine because it fluctuates in that plug there. And you get surges of current in that machine. Well, guess what that does to a motherboard? It fries it. It sure does. Okay? So I said all that to say this. We take the work And then we look at power, okay? Now remember, the work done per unit charge is voltage, but notice we don't get charged for joules, we get charged for what? We get charged for watts, actually kilowatts. So when we go pay the power bill, we are paying for watts, kilowatt hours that we used, okay? So even though electricity is work done on a charge, we're charged by how much power we use. So it's the rate at which we use the energy, not the energy itself. If you don't use much energy, you don't have much power. You use a lot of energy, you're going to have a high power bill. Okay? All right, and yes, people do cheat. I've heard stories out of Marshall Cab where they'll run one wire past the breaker box and run it straight in, and the way they catch them is they'll be checking the meter, and all of a sudden a heat and air unit comes on, but the meter doesn't speed up. Because when that unit kicks on, the old ones had a little dial that spun. Now they're electronic, they're digital. But the old ones had a little dial that would spin, and when the heat and air unit would kick on, it'd go, it'd start spinning faster. Well, they caught people cheating because the dial didn't spin faster, and they basically get a warrant and say, look, we're going to get into your breaker box. And sure enough, they bypass the meter. And then they go back over the years of the power bill and charge them $15,000 or whatever of power usage they didn't use. So don't cheat because you'll get caught. Okay, so now we know how to calculate power. It's real easy, very simple calculation. All right, we can also look at how to determine power one other way. Where's it at? Yes, we can calculate power this way. Now look right here. I gotta hurry. All right, look right here. Power can also be found by looking at the force of acting on the particle times the velocity of the particle. All right, force is what? So we can calculate power this way, watts, the work, dadgummit, divided by the change in time, okay? Or the force times the velocity, okay? What is force? Well, we got newtons, okay? Newtons, and velocity is what? Meters per second, isn't it? Well, how does that work out to be a watt? Well, okay, y'all look. What is a newton times a meter? A newton times a meter is a joule. So a newton times a meter is a joule per second, which is a watt. So yeah, it works beautifully. Okay? So if we know the force applied to the object and we know the velocity that is going along with it, then we can also determine power that way. Okay? Okay. Any questions on that? So we actually got three if you take the derivative, 3 power equations. Okay? All right, let's work some problems. If y'all don't have any questions. All right, let's look at, has anybody looked at these problems?
Are you going to record these problems?
Yes. Yes, I will. Yes, I will. Is it still going? All right. All right. Has anybody looked at these yet? All right, you want to look at number 1? Number 1 is a good one because it kind of gets all aspects of the work done. You want to do number 1? Then I might let y'all work on number 2, and I'll come around and help you. Okay, so let's look at number 1. So we'll do it together, and then let's look at number 2, y'all working on it by yourself. Okay? And actually, y'all, the questions all the way through 1, 2, 3, 5, 8, and 11 are work pretty much, what I'm fixing to do now is pretty much straight out of the gate. Those all the way through 11 that I just assigned are pretty much work the same way, except when you tilt it, that, it doesn't change it much except for gravity. It does change for gravity. All right, so let's look at number 1. Gummit. All right, so number 1. All right. Of course, you always want to draw it. You push your physics book. So and this is what, page 194. So we're going to push our physics book right off a cliff. Is that what somebody said? All right, now. Okay, so we're pushing our physics book. Well, it's a big one, isn't it? All right. And we're going to move it 1.5 meters. So this distance is what? Delta X is 1.5 meters, or S, if you want to put S, that's okay. All right. And we push it, the table out with a horizontal force. So we're pushing horizontally. Force applied is what? Force applied is 2.4 newtons. Okay. While the opposing force of friction is what? Okay, so friction that way, and the force of friction is 0.6, right? 0.6 newtons, okay? All right, how much work does each of the following forces do on the book? Okay, now remember, we're pushing it horizontally. So if we're pushing it horizontally, what is theta? 0 degrees, because this is applied and it's horizontal. Now what if it was pushed at 10 degrees? Then it would be what? 10 degrees, wouldn't it? And all right, now we know work is equal to what? Force, S, or X, cosine of what? Theta, right? Right? Okay, so we want to know what the 2.4 Newton force is, the force applied by the person, right? We just plug it in. Then we got what? 2.4 times what? 1.5 meters. Cosine of 0 degrees. And what do we get? 3.6. Is that easy enough? That's easy. I like work. I mean, work's just, to me, it's just cut and dry. I mean, it's straightforward. Okay? All right, now what's the next one? The friction force. Well, okay. Okay. Well, work. Now look, I'm going to write 2.4 there. I'm going to write friction right there. Work done by friction. Okay, well, all right. We got 0.6, 1.5. Okay, now. And that's, all right, now, ding, 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 ding. What angle am I going to put? All right, the box is going this way, but friction is going which way? What's that angle? 180. So what do we get? Negative 0.9. Right? See, it's easy. It's not bad. But see, remember, how'd you know it, Miss Sheila? Look, the box is moving this way. Friction is that way. Okay? Got to do 180. All right? All right, then what? Normal force and gravity. Oh, come on now. That shouldn't be bad. All right, what we got? C and D? Gravity, yeah. C and D. All right, work done by force normal. Okay. All right. All right, so what is the work done by the force normal? Okay. All right. Well, it's 0. We don't have a weight of the box, do we? But watch this. I'm going to go ahead and do this. Force normal. All right, 1.5. All right. But now, wait a minute. What's the cosine of the angle? Normal force. Gravity. Cosine of what? 90? 0 joules. You with me? That makes sense? Now, again, we don't have a mass, so we can't do a normal force, right? But we do have distance, but we know the angle. See, the angle kills it. See, the angle we know, bam, 90, 0. Right? That makes sense. Okay. Well, guess what it's going to be for gravity? Yep. So we're going to do what? G, 1.5, cosine of 270. And that's 0. Right? Cosine of 270 is 0. All right, then E. All right, work total. Work total, y'all, what do? You just add up work, 1 plus work 2, ... Okay? Okay? All right. So we do what? So we got 3.6 joules minus 0.9 joules. And we get what? 2.7? So we had a net work of 2.7. That's easy, right? Oh man, where's this been, right? Where's this been all our life? Okay? All right, so you do number 2. I'm going to pause it. You do number 2. We might try to squeeze in one more if we can. I'm going to pause. All right, so let's real quick. We said what? We said that on problem 2, it was A was 675 times 10 to the 6th joules, and for the 35 degrees it was 5.53 times 10 to the 6th joules. B is just going to be the negative of both of those. Of both of those. All right, C, we said it's what? 0, right? So we got, was it 1350? Yeah. Times 5,000 meters. Cosine of 270 because it's gravity. 0 joules. All right, now look at number 5 really quick. It says a 75 kilogram painter climbs a ladder that is 2.75 meters long and leans against a vertical wall. The ladder makes a 30-degree angle with the wall. How much work does gravity do on the painter? Okay. All right. All right. 30 degrees, right? Okay. Straight down is what? The painter's climbing up. Okay? He's climbing up. Right? But now, is gravity pulling straight down? Now remember, he's going up. Remember what I said? You always got to reference which direction you're going as to what force we're looking at. So the painter is going up. He's going up, but gravity is pulling this way. So if he was going straight up, then it's the work done by gravity, the angle would be 180, wouldn't it? But he's not. He's going at the ladder's 30-degree incline. So what is my angle going to be? Now remember, this is 30, this is 180. He's going at an angle. So in other words, it's kind of like this. So he's actually going this way. And that angle right there was 30 degrees. So how are we going to find the angle? Huh? All right.
So the 150 is theta?
Yes. Because remember, he's climbing up, but he's not climbing straight up. He's climbing at an angle. If he's climbing straight up, we'd know the work done by gravity would be in the opposite direction, be cosine of 180, but it's not cosine of 180. He's climbing at an angle, and it's a 30-degree angle, so it's 30 degrees off of 180, which is 150. Does that make sense? Okay?
Why would you not do 180 plus 30?
Because, so in other words, he's climbing, he's not climbing because the angle, look, the angle is not 210. Let me draw my triangles.
How do you know to use that 30 or to use like the 60 that it would be also?
It has to be 30 because it was inclined. It's inclined. That's the angle of the ladder with the wall. Because it's inclined to the wall. See, 180, see, look, this is 180. Okay? So he's inclined 30 degrees off of that. So what is this angle? Let me lay it flat. All right, this is 0, that's 180. He's inclined at 30. What is that angle? Now.
Why did you make 180 go straight down?
Because that's the direction of gravity.
Oh,
Okay. See, it's kind of a little, all right, this is where it gets a little fuzzy. When we look at work and then we turn it vertical. Like, wait a minute, I thought straight down was 270. Well, if we're not going horizontal, it's not. If we're going horizontal, yeah. But we're not going horizontal, we're going vertical. You follow me? So see, we got to be careful. We're going vertical. Does that make sense? See how I flipped it over on its side? Now does that make sense? Okay. Whew, I'd think there, man. Oh, how's this going to make sense? All right. Okay? So see, he's inclined at 30, so it's actually 150. Okay? Remember, counterclockwise from the positive x-axis. Where was the positive x-axis? Right there. So whoop, that right there is 150.
You actually get the same number if you do 210.
You will. You will.
Same reference.
You will.
Angle.
You will. Yeah.
Could you use just 30 and just make it -2?
Yeah. You can. You can. Yeah. But again, that's kind of against convention. We like to teach you always orient from the positive x-axis counterclockwise. Or from wherever it's positive counterclockwise. And with work, here this time positive was up. Okay. You could have and made it negative. Yeah. And we get an answer of what? Negative 1750.45 is what you should get. Okay? So how do we do that? So the work is equal, work of gravity is done equal to what? The, all right, now, whoa, wait a minute. What work equation do we use here? We got mass. We don't have newtons. Well, okay, come on, y'all. What is weight? Very good, mg. That is force, isn't it? So we take 75 kilograms times what? 9.8 meters per second squared times what? The height, yeah. What was it? Or the length, 2.75, the 2.75 times cosine of what? 150. Or you can do 30. Just remember it's negative now. Or you could do 210. You could. But really, technically, y'all, that's really not physically correct. I mean, we can say, we get the same answer, but still, it's actually 150. All right. And we get negative 1750.45. Okay? All right. Okay? You see, you got to remember your equations, y'all. Remember, weight is a force, mg. Okay? Weight is a force, mg. Okay? Don't forget that. All right? Okay, y'all. I guess you can go in late. Okay? All right. So number 11 is a similar type problem. It's similar, okay? All right.